In this video, we're going to take a look at trig substitution. Now, in a previous video, we looked at trig integrals, where we were integrating trig functions. In this video, we are actually going to replace a messy looking square root with a trig function. So basically, we're going to look at three types of messy looking square roots. We're going to look at the square root of a squared minus u squared. A here is a real number constant part. U here is a variable part. Or we're going to say a squared plus u squared under the square root. Or we're going to say u squared minus a squared underneath the square root. Notice that there's a difference between this first one and this third one. So if we have these three types, or let me rephrase that, if we have one of these three types, then we can replace this square root with a trig function. And the way we replace it comes from our Pythagorean identities. So cosine squared of x plus sine squared of x is equal to 1. And the equivalent, when you divide both sides by cosine squared, we get 1 plus tangent squared of x is equal to secant squared of x. So if we see the square root of a squared minus u squared, I can take that square root and replace it with an a times cosine of theta. Now, if we do that, then we pair that with a u being a times sine of theta. If I have square root of a squared plus u squared equals a, I let that be a secant theta. And then I'd pair that with u being a times tangent theta. Square root of u squared minus a squared is equal to a tangent theta. We pair that with u being a secant theta. Sometimes you can use the negative square root as well, but that's the basic idea. Now, let me show you where at least one of these substitutions comes from and how it arrives from the Pythagorean identity. So let's take 1 plus tangent squared theta equals secant squared theta. That's one of my Pythagorean identities, obviously the one involving tangent and secant. Well, basically, if I have a constant other than 1, then I can multiply everything by an a squared. So I can multiply coefficients all become a squared. Multiply both on the left and the right by an a squared. Now notice what happens when I take the square root of both sides. When I take the square root of both sides, I get the square root of a squared plus a squared times tangent squared of theta. We use theta here because often x is a variable in our problem, so we'd rather use theta in this case. Now, if I take the positive square root of the left, I can also, this is going to be a positive number, so positive number, positive number. I'll take the positive square root of the right, and the positive square root of the right would be a times secant of theta. So notice that if I let u equals a times tangent theta, if I do that substitution, then the square root of a squared plus u squared. Remember, u is a tangent theta. So square root of a squared plus u squared is equal to a secant theta. And so that's how a squared plus u squared forms. That's why we use a secant theta with that form. And you could imagine if we subtracted 1 from both sides and then did this same process using a square root, that's how we get a tangent is equal to the square root of a squared secant squared, or which is going to be called u. So u squared minus a squared. But just manipulating the 1 plus tangent squared equals secant squared identity can get us one of the options, this form, the a squared plus u squared. It can also give me the form u squared minus a squared, but I have to reverse the roles of secant and tangent. And then the cosine and sine Pythagorean identity gives me the third one, the 1 minus, or excuse me, not 1 minus, a squared minus u squared. So that is how this takes place. So essentially what we're doing is we're doing a substitution where u is equal to a tan theta in this case, or in the other cases, u is equal to a secant theta, or u is equal to a times sine of theta. So that's what we have, all right? If I have this form of the square root, the form of square root of a squared minus u squared, I let that square root be a times cosine theta. And if I did that, then the u would have also had to have been a times sine theta. You can also think of, if I see this type of square root, then u is a sine theta, and then the square root becomes a times cosine theta. If I see this type of square root, I let u be a times tangent theta, and therefore the square root becomes a times secant theta. If I see this type of a square root, I let u be a times secant theta, and then the square root becomes a times tangent theta. So this is the idea. We're going to substitute out the square root with a trig function. And if we do, the u is going to have to have been substituted out with some other trig function. Now, this is substitution, so I still need to be aware of the differential exchange. That differential exchange, just like in the last problem, came from the idea that u is equal to either a times sine of theta, or a times tangent of theta, or a times secant of theta. So I'll figure out the differential exchange as well. Let's do an example. Let's integrate 1 over x squared plus 4 raised to the 3/2 power with respect to x. So we're going to integrate 1 over x squared plus 4 raised to the 3/2 power with respect to x. Now, the form here is an x squared plus 4 to the 3/2 power. 3/2 power is like taking a square root to the 3rd power. So think of square root of x squared plus 4. X squared plus 4, these are both positive. So I'm going to utilize the square root is a secant theta, and a tangent theta is going to be my variable part. In this case, it's nice because we have x squared, so the u can be replaced with just the variable x. So u here is just like x. So I'm going to have x equals a tangent theta, and square root of a squared plus x squared is equal to a secant theta. All right, so here we go. I have x squared plus 4 to the 3/2 power underneath. If I rewrite that, basically what I get is I get the square root of x squared plus 4 all raised to the 3rd power. Okay, let me write that in parentheses. There we go. That's a little bit better. And then I'm integrating that with respect to x. So like I said, this x squared plus 4 underneath the square root is like a squared plus u squared. Now I've written it backwards. 4 is actually my constant of a squared. So here a is 2. And my u is equal to x. But because I have the one where we're adding the two squares, therefore I'm going to let this square root be secant. So the square root of x squared plus 4 is going to be equal to 2 times the secant of theta. I use theta as my variable because I don't want to use x's or u's right here. So I get 2 secant theta is my square root, and therefore my x is going to be equal to 2 tangent theta. So x is equal to 2 times the tangent of theta. Now we're able to replace any square roots with this 2 secant theta. We're able to replace any x we see with 2 times tangent theta. I just need to figure out my differential exchange. And to do that, what I do is I take a derivative of x with respect to theta. I take a derivative of the left-hand side, derivative of x with respect to theta, and then a derivative with respect to theta on the right-hand side. The derivative of 2 times tangent theta is going to be 2 times secant squared of theta. So my differential exchange, I can say that dx could replace, or dx can replace a 2 times secant squared of theta. So that's where what I'm going to replace the dx with. Excuse me, not just theta, d theta. My bad. So the dx is going to get replaced with a 2 secant squared d theta. So think about what that means in terms of my integration. Now we're going to do substitution. The dx gets exchanged with a 2 times secant squared theta, d theta. This square root of x squared plus 4 gets replaced with 2 secant theta. So we're doing 2 times secant of theta. All of that's being raised to the 3rd power. And that's what we get. Now, lastly, once I have done my exchange, once I've done my substitution, then you'll notice that I get a secant squared here. I get secant to the 3rd there. So 2 copies of secant on top will cancel with 2 copies of secant on bottom. There's a single 2 on top. 2 to the 3rd will be 8. So I'm going to get 2 over 8, which is 1/4. And then I'll get 1 copy of secant on the bottom. In other words, this integration becomes something that looks like 1/4 times secant of theta to the 1st power. One over secant, we know that is cosine. So therefore, this integration is just the integration of 1/4 multiplied times cosine of theta. And I'm integrating that with respect to theta. Well, we know what the antiderivative of cosine is. The antiderivative of cosine is sine. So my answer is 1/4 sine of theta plus c. Now, sine of theta is great, but our original integration started with x's. So what I need to do is I need to rewrite this sine of theta with respect to x. Now that's a little bit tricky here because x was equal to 2 tangent theta, and this weird square root was equal to 2 times secant theta. So how do we get sine out of tangent and secant? Well, it turns out since tangent is sine over cosine and secant is 1 over cosine, what you can do is you can say, well, that's like 1/4 times the fraction tangent over secant. Tangent divided by secant. Remember, tangent is sine over cosine. Secant is 1 over cosine. So the cosines would cancel out. Hopefully that makes sense. Let me write this over here. I'm sure some of you don't need this written, but so what we have is sine theta over cosine of theta divided by 1 over cosine of theta. And so in terms of this cosine and this cosine are canceling each other out, and I'm just left with sine. So that's what's happening there. So once you've seen that, we don't have to write that again. Sine is equal to tangent over secant. Now I don't have exactly tangent and secant here. I have 2 times secant and 2 times tangent. So I'll just write a 2 out in front of the tangent. and a 2 out in front of the secant. So 2 times tangent and 2 times secant. Now we're ready to replace. Okay, so we replace 2 times secant with the square root of x squared plus 4, and we replace 2 times tangent with the x. So basically what we're getting is 2 times tangent is the x, 2 times secant, let me write it that way. 2 times secant is the square root of the x squared plus 4. Obviously 1 times x, I put a 1 and a 4 out front because that's what's happening. But if you don't want to write that 1, that's perfectly fine. So that would be my final answer. That is the antiderivative of what we get. So I mean, that is the answer to the question, how do we integrate 1 over x squared plus 4 to the 3/2 power with respect to x? So if we integrate 1 over x squared plus 4 to the 3/2 power, we end up getting x over 4 times the square root of x squared plus 4 plus c. So that's the basics of how trig substitution works. When we see certain types of square roots, we should think those certain types of square roots should be a times a trig function. And we use variable theta traditionally when we do that. That is going to force the u, or the variable part, to be a times another trig function. And then we find the differential exchange off of that. So let's take a look at another example. We have to integrate 1 over the quantity x squared times the square root of 9 minus x squared. So we want to integrate this. Before we go and look at it, 9 minus x squared fits this pattern. So the square root is going to be a cosine theta, and the x is going to be a times sine theta. So we're in this pattern, this first one, with cosine being associated with the square root and sine being associated with the variable. Notice the difference between this one versus the last one. The last one we had x squared plus a squared. This one we have a squared minus x squared. So again, that's why we're using what we're using. Square root of 9 minus x squared. Again, u is equal to x in this scenario. We'll do a couple where u is not just x, but in this scenario, again, u is equal to x. And a squared is equal to 9. So I can say a is equal to 3. So 3 times cosine of theta is my square root. And then x is equal to 3 times sine of theta. Now, if that is the case, then in order to do the differential exchange, we take a derivative of x with respect to theta. Derivative with respect to theta of 3 sine theta is 3 times cosine of theta. And then again, that means the differential exchange will be dx is equal to 3 cosine theta d theta. So just make that a dx, and we get our differential exchange. So now I'm ready to substitute. And in this case, you'll notice that I have a lot of stuff going on. This square root, that is going to, let me just turn into a 3 cosine theta. So that square root turns into 3 times cosine of theta. This x squared turns into 3 sine of theta quantity squared. So replace the x with a 3 times sine of theta. Quantity squared. And then the dx will turn into a 3 cosine theta d theta. Now, there's a lot of stuff going on, but one of the key things you should see is that the 3 cosine theta, and this in the denominator, and the 3 cosine theta in the numerator, this one and this one, can cancel each other out. And therefore, with that canceling out, what we get is 1 over 9 times sine squared of theta d theta. Again, I'm getting a 9 because that's 3 squared, and then obviously I'm getting a sine squared because that's sine squared. So the 3 and the sine get squared, and I get essentially 1/9 over sine squared. This 3 cosine theta cancels out with that 3 cosine theta, and that's what we're left with. Now, right now, this might look like it's hard to find the antiderivative of, but we can rewrite this. 1 over sine squared is cosecant squared. So I get 1/9 times cosecant squared integrated with respect to theta. Now the antiderivative of cosecant squared is a negative cotangent. So I end up with a negative 1/9 times the cotangent of theta, obviously plus some constant. Now, as far as cotangent goes, cotangent is cosine over sine. And the reason I'm saying that is because my original substitution was in terms of sines and cosines. So what I'm going to end up with is negative 1/9. Again, cotangent is like cosine is not like it is equal to cosine over sine. And since my substitutions have a 3 out in front, I'll put 3 cosine theta over 3 sine theta. So there we go. Excuse me. That 1/9 is being multiplied, by the way. So just so we're all on the same page, We're multiplying that negative 1/9 times the cotangent. And now I'm ready to do my back substitution. 3 cosine theta, that was my ugly square root. And then 3 sine theta was my x. So I get negative 1/9. The 3 cosine theta was my ugly square root, specifically the square root of 9 minus x squared. And then 3 times sine theta is just x. And then I can do a plus c. I'll not write that 1 just to make it look a little bit nicer. So that's my final answer. Negative square root of 9 minus x squared divided by 9x plus c is the class of antiderivatives you get when you integrate 1 over x squared times the square root of 9 minus x squared with respect to x. So that's our trig substitution, and it all depended upon using this pairing. This ugly square root, in this case, was the a times cosine theta. The u, or the x in this case, was a times sine theta. And we get that as my final answer. Now, there is one thing I want to mention before we get too far into this. Trig substitution, as we've seen, is a fairly complicated process. It's not a real simple process. So every time you see a square root of something squared minus something else squared, you may want to do trig substitution, or you may not want to do trig substitution. In this case, this one that I'm looking at here, this was something where our normal u substitution would have worked just fine. I could have let u be 25 minus x squared, and then the derivative would be negative 2x. Derivative of u with respect to x would be negative 2x. And I have an x, and so the differential exchange would have worked out in this one, just doing a u substitution. You could do trig substitution if you want, but it's a little bit more complicated. Therefore, if you have the option of doing trig substitution or a normal u substitution, pick the normal u substitution. Let me show you, just remind you how that's done. So on this one, I would have let u be equal to 25 minus x squared, and then my derivative of u with respect to x would have been negative 2x. So if I multiply, again, I think multiply both sides by dx. It's not quite as simple as that. I'd get du is equal to negative 2x dx as my differential exchange. I have an x dx, so if I divide by negative 2, I would get negative 1/2 du can replace the x times dx. So take my integration. This whole thing underneath becomes a u. The x and the dx are going to pair together, and that's going to get replaced with a negative 1/2 du. And then I'm going to write the square root a little bit differently. I'll write that as u to the 0.5 power, whoops, or 1/2 power. And then when I do an antiderivative there, whoops, I would get u to the 1.5 power, and then I divide by 1.5. 1/2 divided by, or negative 1/2 divided by 1.5 would give you negative 1/3. So essentially take 1.5 and multiply it times 2. Now u, if you remember, is 25 minus x squared. So my final answer is negative 1/3 times 25 minus x squared raised to the 1.5 power plus c. So notice that was a lot faster than the types of things we've been doing. All right, this trigonometric substitution, it works really well, and we had to use it in examples 1 and 2. But in example 3, we didn't have to use it. In fact, if you used it in example 3, it would take a lot longer than even examples 1 and 2 would. So if we have the option of doing a normal u substitution as opposed to a trig substitution, we're going to pick the normal u substitution if we can. Now, that being said, in the first two, trig substitution was the way to do these first two. Examples 1 and 2, doing any other type of substitution would not have worked out very well. Would have been more difficult. Not impossible, but more difficult doing anything other than trig substitution. Example 3, you could have done either. So if you have an option, use the easier one. On questions that I would ask you, if I ask you to use trig substitution, then it will be the easiest method to use. It won't be something you could have done easier with a different method. All right. Now, this one you may say, well, this looks very similar to the previous one, but it turns out in this case, this one's easiest to do with trig substitution. So I'm going to ask you to integrate this using trig substitution. If you want to, you can push pause on the video and do that. Otherwise, I'll go ahead and do it in just a couple of seconds. So what we have here is an x squared minus 25 underneath the square root. If I go back to my original slide here, x squared minus 25, that square root should be paired with a times tangent of theta. And that would mean my x, which in this case is called u, is a times secant theta. So I'm using the third option on this slide because it's x squared minus 25. So I wrote that here. Third option, we used in example 1, we use this one. In example 2, we use this one. Example 3, we just did a normal u substitution. So in this example, we're using our third option there. X squared minus 25 underneath the square root. That is going to become 5 times tangent of theta. That is going to force the x to be 5 times secant of theta. Now, here's where things get interesting. When I take a derivative of x with respect to theta, I'm going to get the derivative of 5 times secant of theta. So that is going to be 5 times secant of theta multiplied times tangent of theta. So my differential exchange, it's nice to have either writing on a whiteboard or writing on something like this that can edit real easy. But my differential exchange is that dx can be replaced with a 5 secant theta tangent theta d theta. So that's what's going to replace my dx. My x underneath is going to get replaced with a 5 secant theta. This square root is going to get replaced with 5 times tangent theta. So let me rewrite the integration. On top, just a 1. That x gets replaced with 5 times secant of theta. So that's the x. The square root gets replaced with a 5 times tangent of theta. And then the dx is 5 times secant of theta multiplied times tangent of theta, d theta, obviously. Now, what's going to happen here is the following. We're going to get a lot of canceling out. The secant is going to cancel out with the secant. The tangent is going to cancel out with the tangent. And one of the 5's on bottom is going to cancel out with the 5 on the top. So all we're going to be left with is 1 over 5 to integrate with respect to theta. So this becomes an integration of 1/5, the constant 1/5, with respect to theta. Now, that's just the integration of a constant number, and therefore this is going to be 1/5. My variable is theta, so 1/5 times theta plus c. Now we may say, I don't know what theta is. I know that 5 times secant of theta is x. I know that 5 times tangent theta is this square root. What's theta? Well, here's how we go about that. We say, now I want to figure out what theta is. Usually I take the one without the square root. Usually I take the one with just the x or just the u. And I'd say since x is equal to 5 times secant theta, let me write that down over here. X is equal to 5 times secant of theta. Then I'll actually write down the next page there. Then x over 5 is equal to secant of theta. And that means the arc secant or the inverse secant function of x over 5 is equal to theta. So we replace theta with the arcsecant of x over 5 because x was equal to 5 times secant theta. And so that's what I do. I say, okay, so this means my answer is 1/5 times the arcsecant of x over 5 plus c. Now, this is a really interesting result. What we're saying is that the derivative of arcsecant of x over 5 times 1/5 is actually this weird thing with a square root of x squared minus 25 in it. And if you look that up on some table, you would see that it's correct. But the result here is surprising because we started with some sort of rational type function. This wasn't a rational function because the denominator is not polynomial. We started with something that has 1 over x and then square roots in it. And then when we took the antiderivative of that, we got the inverse of some trig function. Again, that is pretty surprising. Now, a lot of people say, well, how can I find the derivative of something like arcsine? Usually you don't find the derivative of arcsine directly or arcsecant directly or arccosine directly. Usually you actually find the antiderivative of their derivatives. And this sort of cumbersome process allows you to see that the derivative of arcsecant of x over 5 is this thing, is this equation inside. So yeah, so we get arcsecant in short. Now everything so far, we've had x squared plus or minus a number or a number plus or minus x squared underneath our square root. If our u is just not x, but like 4x squared, so let's say we have the square root of 4x squared minus 49, all divided by x, integrated with respect to x. Let's integrate this. So what I mean is the point of this is that so far in all the problems we've done, x has been just my u in all of these. But now I have 4x squared instead of just an x squared. And therefore, the u I'm going to be using is that u is equal to 2x in this case. So if I have a coefficient in front of the x squared, then I have to use that. So 4x squared means that u is equal to 2x. Now it's still u squared minus a squared. So I'm still going to use the square root is equal to a times tangent of theta. So let's write that down. Square root of 4x squared minus 49 is going to be equal to a times tangent theta. Notice that the a is just on this constant part. So this is the a, in this case, since the square root of 49 is 7, a is going to be 7. We're going to get 7 times tangent of theta is equal to that square root. And here's the step we have to realize. U here is not just x. U here is 2x because 2x squared would give you 4x squared right here. So 2x is equal to, again, we're in this third option, third on what I've written down. So we're going to get 2x is equal to 7 times secant of theta. Now there's a number of ways we could go about doing the derivatives. One way is just divide by 2. So that's the way I'm going to do that. I'm going to say x is equal to 7 halves times secant of theta. And then I'm going to take a derivative. Derivative of x with respect to theta is equal to 7 halves times secant theta multiplied times tangent of theta. So the differential exchange is that the dx can be replaced with 7 halves times secant theta times tangent theta d theta. So let's go ahead and do that. The square root, this whole thing, becomes 7 times tangent of theta. The x becomes 7 halves times secant of theta. And the dx becomes 7 halves. Uh-oh. So 7 halves times secant theta times tangent theta. D theta. We're going to get some things canceling out. Obviously, the 7 halves on top and 7 halves on bottom cancel out. Secant theta cancels out with one of the secant thetas. Well, secant thetas both cancel out. And I'm just going to get 7 times tangent times tangent. So we're going to get integrating 7 times tangent squared of theta. Tangent times tangent, tangent squared. Now, you may not have in the back of your head an antiderivative of tangent of squared of tangent squared. It turns out that what you should do is you should use the Pythagorean identity. In this case, tangent squared using the Pythagorean identity is secant squared minus 1. So when I distribute, I'm going to get 7 times secant squared minus 7 integrated with respect to theta. So I get 7 times secant squared minus 7 integrated with respect to theta. I'll put parentheses just so we know that that whole thing's being integrated. Well, what's the antiderivative of secant squared? The antiderivative of secant squared is tangent. So we get 7 times tangent, that's just regular tangent, of theta minus 7 theta, and then obviously tack on a plus c at the end. So 7 times tangent theta minus 7 times theta plus c. Remember, 7 tangent theta was this ugly square root. Let me just take all that. Whoops. So there's my answer, but now I got to back substitute. 7 tangent theta, I can replace that with my ugly square root. Theta here by itself, well, when I divide by 7 and then do the arc secant, I'm going to get arc secant of 2x over 7 is equal to theta. Again, divide by 7 and then take arc secant to both sides. So we get the ugly square root of 4x squared minus 49. That replaces my 7 tangent theta. And then minus 7 times the arc secant of 2x over 7. And then obviously my plus c. So 7 tan theta is this piece. 7 times theta. 7 times theta is this piece. So this is my final answer right here. That square root minus 7 times the arc secant of 2x over 7 plus c. That is the antiderivative of root 4x squared minus 49 divided by x. So you can see that obviously this integration took me understanding the Pythagorean identity. It also took me understanding the trig substitution. This Pythagorean identity is a really nice trick on that. I know the antiderivative of secant squared, but usually we don't know the antiderivative of tangent squared. So use the Pythagorean identity there. That might be obviously hard to see if you've never seen it before, but now that you've seen it, I'm sure you can get it from here on out. Let's do another. Let's integrate 1 over the quantity x times square root of 9x squared minus 16. If you want to take a couple of seconds, pause the video and try this on your own, you can. Otherwise, I will do this in the next couple of seconds. All right, here we go. So we are in the u squared minus a underneath the square root case. So we take that square root of 9x squared minus 16, and we set that equal to, in this case, 4 times the tangent of theta. That means 3x, again, the square root of 9x squared, my u squared is 9x squared. So 3x is equal to u. 3x is equal to 4 times secant of theta. Now, when we divide by 3 and then take a derivative, my derivative with respect to theta is equal to, that'd be 4/3, my coefficient there, Derivative of secant is secant times tangent. Nope. So my differential exchange is that dx is going to be equal to 4/3 secant of theta times tangent of theta times d theta. So that's what we get. And obviously here x is going to be equal to 4/3 times secant theta. So I take my integration and I start doing some substitution. The x is 4/3 times secant of theta. This square root becomes 4 times tangent of theta. And then the dx becomes 4/3 times secant of theta times tangent of theta. With respect to theta, obviously. So notice what's going to happen. The 4/3 are going to cancel out. One copy of secant, one copy of tangent is going to cancel out. So one copy of secant cancels out on top and bottom. One copy of tangent cancels out on top and bottom. And when it's all said and done, that integration becomes 1/4. That's it. So integrating 1/4 with respect to theta. So I end up with 1/4 times theta plus c. I think we can easily solve from here. Be careful when you do that. If I'm solving for theta, when you multiply by the reciprocal, 3/4 x is equal to secant of theta. And therefore the arc secant of 3/4 x, or 3x over 4, is equal to theta. So that's what theta is. So that's all I'm going to do. So my final answer here is 1/4 times the arc secant of 3/4 x. And then plus c. So that's my final answer there. Theta is the arc secant of 3/4 x. So that's what I do. Now, I've always been just solving for this using arc secant or arc tangent or arc whatever. It turns out that if you want to, we can solve for arc cosine as well. Since secant is 1 over cosine, you could have said, oh, this is 1 over cosine theta, and then solved it for arc cosine if you'd like. Or if you really wanted to, you could have used arc tangent with this equation. So we could have solved for arc tangent with this equation. So there's multiple ways of writing the answer. They're all algebraically equivalent, but I just solve for arc secant usually. And I said arcsequent. Let me rephrase that. In this case, we had x is equal to something times secant, so I solved for arcsecant. If I had x is equal to something times sine, I'd do the arcsine. If I had x equals something times tangent, I do the arctan. So whichever one of these scenarios I'm in, I solve for whatever that scenario gives me, to be clear. Let's do another. Here's example 7. As always, if you want to push pause on the video and try it on your own, you're free to do so. Otherwise, in a couple of seconds, I will do this. So with this one, trig substitution is the way to go. And we have a squared minus u squared, where u is equal to x once again. That's always nice. By the way, oftentimes these numbers, I've always given perfect squares here. But if this number was not a perfect square, then you just take a is equal to the square root of whatever this is. So in this case, a is going to be 4 because the square root of 16 is a nice number, which is 4. But if you had 170 instead of 16, then a would just be simply the square root of 170. All right, so square root of 16 minus x squared, that should be equal to 4. So we're in this, the second one I've listed, 4 times cosine theta, because again, constant minus variable squared. So 4 times cosine theta. And that means my u, which in this case is just x, is going to be 4 times sine of theta. Now the derivative of sine is cosine. So if I do 4 times cosine theta, I get the derivative of x with respect to theta. So my differential exchange is going to be that dx is equal to 4 cosine theta d theta. Notice what happens here, interestingly enough. This square root is going to be replaced with a 4 times cosine of theta. The dx is also going to be replaced with 4 cosine theta, but times d theta. And that integration is just the integration of 1 with respect to theta. So I just get 1 theta plus a constant as my set of antiderivatives. Now, theta here, hopefully we can see, but I guess I'll write it down. Probably easy to do in your head, but x over 4 is equal to sine of theta. So that means the arc sine of x over 4 is equal to theta. So arc sine of x over 4 is equal to theta. And that means my final answer is the arc sine of x over 4 plus c is the antiderivative of 1 over the square root of 16 minus x squared. So 1 over the square root of 16 minus x squared integrated with respect to x gives me the arc sine. Once again, I'll just point out that is pretty surprising because we have this square root of a polynomial and I end up taking the antiderivative, and the antiderivative of that is some inverse trig function. That's a really, again, weird result that 1 over the square root of the polynomial has antiderivative of the inverse of a trig function. Again, just surprising. Now, that one had, the previous one had 1 over the square root of 16 minus x squared. What if we just change the sign underneath the square root from a 16 minus x squared to a 16 plus x squared? Would we get something similar? Would we get something different? Would we get something crazy altogether? Well, let's go through this one using a plus instead of a minus. Obviously, if you want to try it on your own, you can, but well, I'll just do it right now. So 1 over square root of 16 plus x squared integrated with respect to x. Now, since that is a plus, what we're going to be using is the one where we let a times secant of theta be the square root, and x equals a times tangent theta. So a secant theta is going to be that square root because of the plus. A tangent theta is going to be the u. I always start with writing the square root first because that kind of determines which one you're going to be using. So 16 plus x squared is equal to 4 times the secant of theta. And then that means x is equal to 4 times the tangent of theta. Again, that's because we're in this first scenario type of square root. So we have this first type of square root. That means the square root is a secant, and then the x in this case is a tangent. Now, if I take a derivative of tangent, that's going to be secant squared. So my differential exchange is that dx is equal to 4 secant squared d theta. And now I'm ready to substitute. So this entire integration, the dx is going to get, I'll do that replacement first. That's going to get replaced with a 4 secant squared of theta d theta. The square root is going to get replaced with a 4 times secant of theta. And so we see here that the 4's are going to cancel out. one of the secants on bottom is going to cancel out with one of the secants on top, and we're going to get essentially 1 times secant theta as what we're trying to integrate. So we're integrating basically secant of theta with respect to theta. All right. So that's what we're integrating. Now, I'm just going to give you the antiderivative of secant, but I'll show you how I got that in just a moment. So let me write the antiderivative of secant. The antiderivative of secant is natural log of secant of theta plus tangent of theta. So we got natural log of secant plus tangent plus c. And then I'll give you my final answer here, and then we'll come back to how I got natural log of secant plus tangent. That's a very interesting trick to go from secant to this. So secant, oops, secant is the square root over 4. Tangent is x over 4. So what I'm going to do, oof, went too far up and too far down, is say that is the natural log of this, like I said, secant is the square root of 16 plus x squared over 4 plus tangent is x over 4 and then plus c. I'm using parentheses around the natural log argument. If technically you should probably use absolute values, but there we go. That's the whole thing. So obviously one of these, when we use 16 minus x squared, that was a much, much easier problem. Just came out to arc sine. Much easier to do than a 16 plus an x squared. So this is just to say, be very careful of the difference between plus and minus and those types of things. Now, if you want to figure out how I came up with this as my antiderivative of secant, one way you could look it up, but the other way is actually using a lot of tricks as far as integration tricks and trig tricks. So basically what you do is you take secant of theta and then you multiply on top and bottom. So this is a well-known trick. By secant of theta plus tangent of theta. Okay, so you do that on top and bottom. And then d theta, obviously. You're taking the integration with respect to theta. So multiply on top and bottom there. And then we're going to expand out. So in the numerator, we're going to get secant squared of theta plus secant times tangent and then in the denominator, we get, again, secant of theta plus tangent of theta. So, sorry if that makes sense, d theta. And once you do that trig trick, then what happens is you do a regular u substitution. You set equal to the denominator, and then the derivative of u with respect to theta turns out to be, well, derivative of secant is secant times tangent. The derivative of tangent is secant squared. So notice that the derivative is exactly what you get as the numerator of this fraction. And so if we take the numerator of that fraction and multiply it times my d theta, that all can be replaced with a du. So this entire integration, which remember is equivalent to secant of theta, is just, well, the numerator times d theta becomes a du, and then the denominator just becomes a u. So we're just integrating 1 over u. So we end up with natural log of u plus c. And then remember, the u was simply secant plus tangent. So the antiderivative of secant becomes natural log of secant plus tangent plus c. So that's how you find the antiderivative of secant. Notice that's why I didn't want to write it all in the problem. All right, so antiderivative secant becomes natural log of secant plus tangent, quantity plus c. So if you know that little trick, then this is easy. If you don't know that, that's real tough, okay? That's a real tough integration if you don't know what the antiderivative of secant is. But now you do, and so that's what it is. So notice that again, 16 plus x squared under the square root was a lot more difficult than 16 minus x squared. So be very careful of your pluses and minuses because they can really give you a lot of different answers. And they can also make your problem much, much easier in this case where we had the minus, or much, much harder in this case where we had the plus. Let's do one more example of trig substitution. Here I have 1 over x squared plus 1 integrated with respect to x. Now I don't have a square root, but what we could do is think of x squared plus 1 as the square root of x squared plus 1 quantity squared. And that's what we're going to do. So that's what I'm going to do. I'm going to think of this thing, square root of x plus 1, x squared, plus 1, squared as just x squared plus 1. So I'm going to think of that way. And in that case, Now I can use my trig substitution. So we have a plus in there. So that is the first one. I'm going to let 1 secant theta be that square root. So 1 secant theta is just the same thing as secant theta. And then the x is going to be 1 times tangent theta, which I'm just going to call tangent of theta. The derivative of x with respect to theta, derivative of tangent, is secant squared. So my differential exchange is that dx can be equal to secant squared of theta times d theta. Now look at what I have here. The square root is equal to secant of theta. So I replace that big square root with secant theta. My dx I replace with a secant squared of theta, d theta. And so secant squared in the numerator is going to cancel out with the secant being squared in the denominator. And I'm just going to end up with the integration of 1 with respect to theta. So I get theta plus c as the antiderivative. And then I remember what this did. So x is equal to tangent of theta. That means arctangent of x is equal to theta. So this is the arctangent of x and then plus c. So the antiderivative of this rational function is arctangent. And that's, again, a pretty strange thing. Excuse me. We have a rational function, and the arctan is the antiderivative. And then on the other side, if I would have taken the derivative of arctangent of x, we would have gotten this weird rational function. And again, that seems pretty weird in certain senses, that the inverse trig function is somehow related to a rational function with the instance of derivatives. But this is what we were looking for. This is the final answer here, this one. So we've went over a lot of different trig substitution problems in this section. So obviously we've done a lot. We haven't done every single one. Things can get more difficult, less difficult. We've seen how to get arcsecants and arctangents and arcsines. Lots of different interesting cases here. I've always been using the positive square root. There are times when you may want to use the negative square root, but if you're in one of my classes, you can just assume and use the positive square root if you're doing that. So that's the idea of trig substitutions, substituting out with a trig function. And in the next section, we'll see some other some other integration techniques as well.